Your screen is invisible. Yes.
Where do I put this? Okay, I'll disable that.
Yeah, it's kind of mandatory. Like,
I think it just happens automatically. There is something, and people don't realize it, and they start, you know, scribbling on this thing.
basically, once it's just going to be happen, it is going to be so fun. Like everyone just doing again and again. It's
But then,
like you're doing.
how do I remove this?
Sir, there will be more option. In the shared screen, at the top, there will be more option. Just click on that. Then there will
Mhm.
be option called stop annotation for everyone
No,
others.
that I have stopped, but this line is there, na?
Okay,
This,
okay. There will be pen type of sign in the right, left hand side at the bottom.
yes,
Just click on that and take eraser and erase it. So
yes.
yeah,
Okay,
yes,
finally.
just now it's done. Yes,
Okay, too many tricky things.
yes.
Okay, I'll move it on the side. Hopefully, it won't disturb us. Okay, so screen is clearly visible, right?
Yes, sir. It's visible, and we are live at the same time. So yeah, both things are fine, sir. Can we start, Pranav?
Yeah, it's 7:03, so we should get started.
Okay. There is a lots of people on the YouTube.
Okay,
Yes, yes.
we'll try to take some questions towards the end and see if I'll be able to answer some of them. Um, so good evening, everyone. Today we are going to talk about Indian Chandrayaan missions. And as you know, we have so far three of them, one, two, three. And some of you probably know this that I have worked on Chandrayaan 1 data and published a paper, and my I got little bit popular. Uh, so the thing is, my photo was on the newspaper and everywhere else. So it was a fun time. It was in 2009-10 when Chandrayaan 1 almost ended, basically. The mission ended in 2009. So we'll see some of the results from that work. And then we'll also see like what different missions we have, and how they have progressed over time, and what we have actually learned from them. So all those things we are going to learn today and see. Of course, I'll not go into too much of technical details, because then I guess it becomes a little bit boring, I guess. So if you have any questions, you can let me know. I'll try to answer them, as I said. So let's get started. Okay.
Yes, sir.
Okay.
You can continue, sir.
Yeah. So yeah, I was trying to find the controls and all. It's okay. I found them. Okay.
Okay.
So why do we explore moon? That is like the first question which a lot of people ask me all the time. And there is no one answer, of course, but simple is that it's a very natural laboratory and very close to us. And it is closest to us, actually. All other planets, moons, objects in our solar system, are further away. So it will take a lot of time to even go there, record something, get the data. That is why we are able to send humans to moon itself, but not to any other planet. When we say we like the humankind, right? Not just India. So because science belongs to everyone. So that is a very good natural laboratory we have. And as you can see, few things here, I have listed. So we can learn about early solar system history, because moon doesn't have any oceans, no atmosphere, not much activity is happening, no earthquakes like thing, moonquakes we don't get. So because of that, it is like preserved for millions of years, or I should say billions of years now. So it's a very good, pristine object which we have very close to us. So we can study history of our solar system. It has recorded impacts, volcanism, evolution. Crustal means upper crust layer. Polar regions are permanently shadows, so they trap volatiles like ices, which we have detected again from Chandrayaan 1 mission, the first confirmation which we got of water ice. And then Moon is, as I said, also a laboratory for testing navigation, landing, robotics, other planetary science stuff which you can do. Maybe in future we can have like a base where we can launch missions. So those things are there, and also it prepares us for deep human and robotic exploration in future. So this is a very interesting image of moon, I would say. So left hand side, what you are seeing is the near side of the moon, and the right hand side is the far side of the moon. Sometimes the far side is also called the dark side of moon, but it's a wrong name. But a lot of movies and places like that use this name, like called dark side of moon. But it is incorrect. Why it is incorrect? Because it gives an impression that if it is dark side, that means the other side never receives the sunlight, right? And it's always dark. But it's not true. The thing is, it's near side and far side. The near side is the face which we see from Earth, and that is the only face we can see. It is our limitation because of geometry. Why geometry? Because moon takes exactly 28 days to rotate, to make one rotation. Like Earth take 24 hours, you'll know that. But moon takes 28 days. It's very slow. But at the same time, moon takes 28 days to go around the Earth, one revolution, one orbit. So because it is 1:1 synchronization, and it is with a lot of moons in our solar system, like Jupiter moons, other moons, they are also synchronized like that. So because of that, one face is always visible to us, and that is what we call as near space, the near side of the moon. The right hand side is the far side, and you can see they are very distinct in nature. And the when you look at the moon and you see some features, right? Some dark patches. Those dark patches are these regions which you actually see on moon from Earth also. Once when you look at the moon when it is full moon. So don't get confused. The other side also receives sunlight. It's just we don't get to see it when that side is receiving sunlight because this side is on our side. So we get to see no moon day, right? So Amavasya, which we have. So no moon. So this is how it is. So all the sides receive sunlight of moon. Uh, all right. So moving ahead. So if you talk about our lunar program, so first Chandrayaan 1 was sent in 2008. It was only an orbiter. Orbiter means which orbited around the moon. So there was no lander or rover. Lander is like which goes and sits at a place. So lander, and rover is which goes around. So as you can see, there was a huge gap between 2008 and 2019, almost 11 years. The next one. This one we had planned for orbiter, lander, and rover. But unfortunately, as some of you already know that the lander and rover thing didn't work because of some issues, which I'll talk in a bit. And then Chandrayaan 3, which was launched just few years after that, to rectify these things and fix the landing part so that now we have lander and rover operating actually. And I'll show you some images also. So just wait. So this was the idea. So what Chandrayaan 1 did, let's start with first one. So we got like a mapping orbit of about 100 kilometer. So we went very close to moon. It was like 1,380 kilograms of orbiter. Uh, uh, and as I said, it went very close to moon, almost 100 kilometer to the surface. So we got a very high resolution images. I'll show you some images also, which I generated and which the paper got published. So it was in 2008 using PSLV. In case you don't know what PSLV is, it's Polar Satellite Launch Vehicle. Okay, and C11 is just model and all that. So we got to go know chemical, mineralogical, geological mapping. Geology means like how the surface is, how much up, downs are there. So all these things, different types of rocks. It carried 11 scientific instruments from India and also international partners. So we had instruments from USA and other places. It also had a Moon Impact Probe, MIP, which was released in 2008 November, and it hit the moon eventually. It hit the surface of moon, and it crashed. But while doing it, it got a lot of measurements, images, and all that. We were able to capture about 3,400 orbits of moon before we lost communication, and the mission was lost in 2009. So moving on, this is the research which I did when I went to ISRO to do my research at that time, 2009-10. So these are the two orbits of data. I'll show you, I'll zoom in a little bit because I'll show you like what actually is there. So as you can see, there are some craters, right? And here, if I go, the southern hemisphere, this is a Tycho crater, you see. This is a very interesting and crater because it's a very old crater. Okay, and I was lucky enough to get a orbit where I could get this Tycho crater. So studying it is very important for studying moon and all, and also understanding the evolution, which I told you guys earlier. So I was able to study this Tycho crater, and I'll show you some images which I generated. So this is just from top. And also we got a lot of craters here. And if you see on here, this is more of a Murray region. Murray means lowlands of moon, which were resurfaced by the volcanic activity when the surface was heated up long time back, some billion years ago, right? Recently, nothing is happening. So moving on, I'll show you some result as I told you. So on the left hand side, what you're seeing is the mineralogical map of moon of the Tycho crater. So this is the Tycho crater at the center. I'll get the pointer. So this is from an older NASA mission, actually, Clementine, if I'm correct. And this right-hand side is the image which I generated using our Chandrayaan mission. And as you can see, you can compare these two images and you can clearly tell how beautiful this right-hand side image is, how much more information we are getting, and how detailed it is. You see this part, here it is almost flat, right? But on the right-hand side is way more detailed. So that is what we have achieved with Chandrayaan 1 mission. So this was very good at that time. And these are the spectral profiles. So spectral profiles, if you don't understand, don't worry about it. It's just like a signature. So we all have signatures, right? So every person has a different signature, no matter how close relative you are, no matter who you are. But your signature will always be slightly different from somebody else, right? It's like DNA, you can say. So what happens here is uh, when you look at something, it reflects some energy. Okay, material reflects energy. So you receive this reflected energy and you plot it. So x-axis you are seeing wavelength. It's in nanometers. So 400 nanometer is blue, 700 nanometer is red, above 700 is infrared. So here what you see is the features. So you can see there is a feature, and 1 2 3 4 is just different locations. 1 2 3 4. So one is for one orbit, another one is for another orbit. So two I wanted to just show you, just so that you get some idea like how reflective it is. So as you can see, out of, let's say, 1 unit is incident, so only 0.18 is reflected, or 0.14. That means the reflection is only 14%, 15%, 10%. So it's very, very low. And overall, moon only reflects 11% of total energy incident on it. So out of, excuse me, so out of 100%, whatever it receives, only 11% gets reflected. The rest of it gets absorbed by moon's surface. So this is all the research which I had done while I was in ISRO. Now let's come back to overall perspective, like what we actually missions in this mission, what kind of instruments which we had. So as I mentioned, there were many of them. So I used this one, IC, or hyperspectral imager data. This was good for mineralogy. So I showed you the mineralogy map actually. So in that map, I'll go back. As you can see, different colors. So different colors actually indicate different minerals. So one is indicating silicon oxide, feldspar, another is indicating titanium oxide, and one more is there. So different minerals indicated by different colors. So you get to see that lighter colors are thrown out and they are further away from the central area. Central area has heavier elements. And it's obvious because if there is an impact, the lighter material will be thrown further away, right? So this is like the spray you see is because of the impact which created this Tycho crater, and center you have a peak. So this is what we learned from Sahaisi. Then mineralogical mapper M-Cube gave us this water signature, and M-Cube was a US instrument, not ours. TMC was terrain mapping camera, that was ours. Then we also had a radar, mass spectrometer, and energetic neutral atoms. So you want to basically study everything. Topography means the surface features, and polarize, lunar exposure, and solar wind interaction. So all that we have studied with Chandrayaan 1. It was a very successful mission. Uh, am I audible?
Yes, sir. You are audible, sir.
Okay, I think I lost connection. Anyways, so this M cube, as I was mentioning earlier, was responsible for detecting these water or OH signatures. So basically, it detected hydroxyl molecule, which was indicative of water-related signature. So there was no direct detection of water molecule. It was this OH molecule, and indirectly it tells us that there must be some water molecule present. Okay. Mini SAR or SAR synthetic aperture radar provided evidence of subsurface water ice in permanently shadowed craters, which are permanently shadowed because of the geometry. They never see sunlight. Chase detected water molecules in the tenuous or exosphere. Don't get into the technicalities. Even if you don't understand, it's basically some particles or these volatiles, they get up from the surface and they surround the moon. So that basically transformed our view of moon as a completely dry world. And now we have water and water signature there. So other scientific outcomes, of course, we got a 3D terrain map, which I showed you earlier, like very beautiful detailed map. Solar wind means we got to learn about sun, solar wind. We are also learned about lunar geology, like how the oceans, magma oceans were there and all those things. We also future uh, candidates for landing and missions were planned using this mission. So it was a very successful mission, as I said. Moving to Chandrayaan 2. Chandrayaan 2 was like the next step. So basically goal was to have a soft landing of Vikram lander, and Pragyan was like supposed to be a rover, and orbiter was also there. So it was sent in GSLV, a more stronger, bigger rocket. Okay, geostationary launch vehicle, in case you don't know. So it had 8 scientific instruments. Then Vikram carried thermal and seismic because you want to study surface activity. Pragyan to do in situ elemental analysis, so it can go around and do these in situ, get some samples in situ measurements. And orbiter, of course, has to remain in the orbit and collect data from Vikram and Pragyan and then send it back to Earth. That was the whole idea. But of course, once we reached around 2.1 kilometers, so I was there working at that time in PRL, which is subsidiary of Department of ISRO, which is basically ISRO, Department of Space. So it was happening all in front of me at that time. So we were very excited that this is going to land, but unfortunately, we lost the communication at around 2.1 kilometers just above the surface. So it was very close, and then it crashed basically. So descent was very fast as compared to what we planned. So it was a hard landing, and the orbiter, of course, was there. It continued the scientific mission, so all was not lost. People think it was a failure, but no, it was not a failure or failed mission. It was a successful mission up to the orbiter part. Of course, we lost lander and unfortunately the rover along with it. We could never make the contact with it, but still the orbiter gave us a lot of new scientific discoveries and ideas which we learned from the orbiter instruments. So what we achieved from Chandrayaan 2, as I said, it was a failure, but not a failed mission. So we got to, again, a good successful launch we achieved. Successful separation from the orbiter, this lander. We also continued operating this Chandrayaan 2. The camera provided a better imaging capability. So now we have a 0.3 meter resolution images. Also, a lot of scientific data, as I said, was collected. So it was designed to be more tolerant and to the conditions. And as I mentioned earlier, Chandrayaan 1, we lost very early as compared to what we planned. So Chandrayaan 2 went along for a very long period of time. So of course, some success, not 100% success. And of course, we learned one more thing, that planetary landing is a very tightly coupled control problem. That means a small change or deviation in navigation, propulsion, sensing, software here, there can lead to large errors. So you have to be very, very careful. So we designed Chandrayaan 3. We sent it in a different mission, different rockets, LVM, and this was successful. Finally, we landed in near the southern pole, which was this coordinate here, 69.37 south and 32 degrees east. And Vikram and Pragyan are still operational. It has operated about 100 around the lander. We achieved the soft landing, and it was a successful mission in 2023. So that was success. So what did we learn? As I said, it was a failure, but we got to learn a lot of things. So first, we have increased the landing area. We chose a bigger area, so provided us flexibility for spot selection when we get there, because you don't plan everything like by inch by inch. So you get there and then you maneuver. Engine configuration, we made it simpler, less dynamic error. Attitude correction. So attitude is not altitude. Altitude is height. Attitude is different. Attitude is like once you get somewhere, there is an error in the orientation, let's say, or navigation. So you can fix it. But earlier, it was only 10 degree per second. So that means, for example, let's say, if there is a error of 30 degrees, it will take about 3 seconds to get it aligned properly. So that's a long time. But with Chandrayaan 3, it was 25 degrees per second. So you could adjust for 25 degrees in 1 second. So that's way faster, right? 2.5 times faster. So that made it more accurate. Also, landing leg structure, we changed it a little bit. So it was initially standard one, but we have reinforced tolerance to it. And then sensor suite, we added this Doppler velocity meter. So what it did, it provided a direct 3D velocity vectors and more detail about everything what is happening. So this is how engineering learns. So you should never be afraid of failures. In engineering and science, you should be ready for failures, because if you fail, you will learn new things, you will apply it, you will become successful, right? So next time you can do something better. All right. So moving on, here is the planned mission. So it has started from Earth. Slowly, we made it bigger and bigger, the orbit, more elliptical, and then eventually we pushed it a little bit when it reached here, and then it was transferred to lunar trajectory. And slowly, we went more circular and got to a moon-bound maneuver. And here, the landing was achieved. So this is the image of the Vikram lander taken from the Pragyan rover on August 30th. So 7 days after we landed. So it took some time to capture some cool images. So as you can see, the Vikram is sitting nicely there, and the rover is somewhere here and taking that image. Few meters away, took this image. Nice and beautiful, as you can see, the lunar surface. Uh, Moving on, so Chandrayaan 3 had all these suits: chest for thermal properties, ILSA, seismic activity, again, Ramba for plasma environments, LIBS for composition, laser spectroscopy, like the spectra I showed you. So get like spectra in situ, not from distance. You take the sample and you take it. And then elemental composition using X-ray spectroscopy. So different spectroscopy, same idea. Shape for polymetric view of Earth, all those things. So remote sensing, landing, and then eventually we got this direct surface measurement. So why South Pole? There's a question. So the thing is, South Pole has a very unique case because as our South Pole, the angles are very extreme. So they create extreme illumination conditions. Okay. Some craters also have this permanent shadow region around the South Pole and North Pole only. Okay, so cold traps are there, so you can study them in situ again. Also exposes to ancient highland material. Also direct measurement from a high latitude, which is very useful for understanding geology, thermal environment, future exploration also. Because once you get to the far side, you will get solar energy, but the problem is the signal transmission, because the same side faces the Earth. So how will you transmit the signal through the moon? It's very difficult. So you get to learn all these things. So further you go, further more improvement and more learning you get. All right. So how do we get clues? So you get like local soil from APXS instrument, then major elements you can get. You get a geochemical interpretation, like how highland material is there, lowland is there, Mare region, which I told you earlier. And you get to clues to crust, upper mantle. So this is, if you remember, our PM gave this name, the point as Shiv Shakti point. So that's where it landed. So it suggests that we have access to this very primitive, means very initial early days mantle related material from this landing and rover site. So exciting days ahead, a lot of research is coming up. So some key takeaways I'll tell you. Chandrayaan 1 changed our science by establishing strong evidence of water OH on moon. Chandrayaan 2 showed us that lunar orbit and orbiter science can be succeeded. Even if we failed, it's okay. And then it became an engineering input for us. We learned a lot of things. But of course, we learned, we improved, we went again, and we demonstrated that, okay, we can do a soft landing also very close to South Pole, which is also very challenging because to get to South Pole, it's like orbital challenges are there. You have to maneuver very sophisticatedly. So all these things are there. And then mission illustrate, like we get remote sensing, then to landing, and then we eventually got in situ measurement. And then we can connect all these things. And that way we can get better understanding of planetary science, planetary evolution, our evolution of solar system, and all these things by taking a small step at a time. So that's why, that's how you do planetary exploration, basically through iterations, small steps at a time. So that's all from me. Thank you very much. I hope it's not too much of knowledge packed in a very small amount of time. But I finished it fast because I'm sure you guys have a lot of questions, and I would be happy to take some questions and answer them rather than me just talking, right? So thank you.
Yeah, so it was really nice as usual. There is a lots of students are who just going to ask you the questions. So I'll just ask everyone to please raise your hand if you're having any queries, everyone. Please, just raise your hand, everyone. If you're having any queries, please raise your hand. Okay, Isant, nice. Yes, Isant, you can just ask it out. Wait a second, let me just.
Yes, go ahead.
Wait a second. You need to turn on your camera as well, right? Yes. Now you can just do that. Please turn on your mic and camera. You can ask it out.
Am I audible, sir?
Yes, yes, you're on well.
Yeah. So my question is, we know that at the time of Chandrayaan 3, there was one mission of Russia ongoing, which is also called Luna 25.
Mhm.
So we know that our Chandrayaan 3 mission succeeded, but at the same time, the Luna 25 failed of some reasons.
Mhm.
So what are that reasons of Russia's space satellite?
See, no country is going to release all the reasons. Like, for example, we just said there were technical glitches, right? What are the actual reasons? What actually went wrong? Nobody is going to share. So it just didn't work. That's it. So, and
Yes.
yeah, these are sensitive informations, no? So no country is going to share the actual reasons. It will always be like technical glitches, right? So yeah. Anything else?
And sir, what are the major benefits of Chandrayaan 3 that we get from Chandrayaan 3?
Yeah, so major benefit of Chandrayaan 3, as I mentioned in my presentation also, is that in situ measurements. In situ measurements are very, very crucial in any type of science exploration because how will you confirm? Let's say I'll tell you that there is this mineral present, but how will you confirm? There has to be some confirmation, right? So we have a lot of confirmation on lunar science from these Apollo missions, which earlier NASA sent, no, those these people who actually went there. Neil Armstrong and all. So they collected a lot of samples and they brought it back and we studied them in the laboratory. And that's what give us all the basis about the surface geology and mineralogy and all that. So we want to do it more because Apollo missions again are very limited. One location, you collect some sample, you come back. So that is the major advantage of having this Chandrayaan 3 mission, that we are able to do it in situ. There is a rover which can go around, take measurements there, then move on to the next location, again take the measurement, compare, see how it works with remote sensing measurements. So whatever we know so far, whether how correct it is. So
Yeah.
that kind of we say is as ground truth.
Yes, sir.
Okay, next person. Because there are so many, right?
Yeah.
Okay. Yaza, please ask it. Hello. Yathak J. Wangsa, please. Turn on your mic and ask it. Hello. Yes,
Yeah,
please ask it.
you have to unmute yourself and speak. Yathak. Hello, Yathak, you are not audible.
Okay. Until then, we'll just take the question of Abhimanyu. Abhimanyu, please.
Wait,
Sir,
yeah.
in the Chandrayaan 2 means partial failure.
Mhm.
That was it software glitch, communication glitch, or something else? What glitch was there?
I cannot tell you. These are sensitive information, I told you. We cannot publicly tell what actually went wrong or what actually happened. Uh, but just assume there was some technical glitch because it went too fast uh, than planned. So it crashed, basically. Okay.
Any other question,
Okay, sir.
Abhimanyu?
Thank you, sir.
Yeah, next person. Let me read one. In your mapping of Tycho crater database, how did you mathematically resolve the topographic effects and variations in the solar illumination geometry using the high resolution TMC digital model to avoid false positive? Okay. Okay, that's a very heavy question, Lakshmi. The thing is, there are a lot of softwares available, but at that time I was very new to all this. So I used a software called NV. I'll put it ENVI. Okay, sorry, I put wrong spelling. NV. Okay, so it's called NV. So it's a very good image processing software to do all these kind of things. So you can basically map, you can change the orientation, you can change the resolution, you can fit data. So it does a lot of things for you. So at that time, I was not very well accustomed with coding as much. So I didn't design any code or program for it. I basically used the software to do all these kind of things. But yes, all these things have to be fixed, like avoid false positives and illumination effects and all that. So we use the software basically because I only had like 1.5 month also uh, as summer intern. So I couldn't, develop everything from scratch. I just use whatever resources were available. And the idea was just to, show others like what we have achieved. So that was my idea. So I published those images. All right, next person.
Hello, sir.
Yeah.
Yes, sir. My question is,
Mm,
sir, what is the biggest unsolved engineering problems in
mm.
human space exploration today, and how do
Wow.
you think AI and robotics changing the role of astronaut in the next 20 to 30 years? And
Mhm,
then, if you are a students
mm,
students starting an aerospace career today,
mhm.
what skills would you focus on developing, sir?
All right. Wow. So many questions. Okay, so I don't know the biggest problem currently we are facing. There are many problems out there. For example, how do we can send humans to Mars? It's
Yes.
practically not feasible because it's very long journey. One way is like 18 months. What will you do? So, uh, That is one problem. Another problem is how do we explore deep space, right? It's everything is so far away. Like, how will you send something which can study deep space in real time? So there are many problems, many big problems out there, and then there are small problems like power sources. Somebody asked a question about using nuclear power. Nuclear power is not very easy to use because it can damage other equipments, right? So those are the things. There are many things. Then the AI and robotics, of course, it is going to play a huge role in future missions because you if you are sending a robot, uh, you don't know 100% what is there, right? So you want a robot or your mission or rover, whatever it is, to adapt, and how it will adapt using AI, right? So that's what you want. So a lot of research is being done using AI and robotics, and we have a lot of competitions like not mission Mars rover teams are there. They compete, they design better and efficient rovers for Mars. So engineering problems are there. So better robotics are needed, more efficient robotics are needed. And of course, AI is there. So that is also required. And your final question was aerospace. So aerospace is huge again. If you want to learn aerospace, learn rocket science, and not just rocket science, learn celestial mechanics. That is very crucial. No matter if you want to go into this field of rocket engineering and all that, learn celestial mechanics. It's very important, or we call it orbital mechanics sometimes. Orbital mechanics is very crucial. Everything is designed like maneuvers, navigation, X, Y, Z. Your GPS work only on Earth. There is no GPS on Moon or Mars or anywhere in the universe, right? So it's
Yes.
very crucial to study the celestial mechanics and all, and get into that direction and work on those things. So I guess I have answered a lot of things. Let's move on to the another one.
Hello, sir. I'm audible.
Hmm. Yeah, tell me.
Sir, as you said that when Chandrayaan 2 is happening, you are there, as you said.
Yeah, basically we were watching
Yeah,
the screens kind
yeah,
of
yeah.
thing.
Like,
Right.
like, do you have any, like, what was the decision that you have to make at that moment? Any moment?
See, we were not making any decisions. See, there are different teams for any mission. There are multiple teams. Okay. So one team is like science team. So we were mostly part of science team. So science team is like, okay, we tell engineering team, then there is engineering team. So we tell engineering team that we want to do this research. So please design an instrument which can do this work. So the engineering team will design it. Then there is a launch team. So launch team will launch it. So so all communicate with each other. So launch team will tell what is the limitation of our mission, how much weight we can send, how many payloads we can send, how many instruments we can send, right? Then accordingly, engineers will design it. Then engineers will tell us that okay, your we cannot achieve this because we have this limitation. So please modify your objective. So then we modify our objectives according. So that's how it works. So the launch team, we are not allowed to go in there. We are
Yeah.
outside. So we cannot make
Hmm.
any decisions. Once the launch starts, the launch team takes over. So they will decide whatever needs to be done. Once it lands and mission is operational, then there is a data processing team. So there
Yeah,
is a
yeah.
different team. So then the data is sent to that team. They will process the data and then they will send us the data. That okay, now you have the data,
Hmm.
you do the science. So that's why we are working together, but we are not interfering in each other's work also. So that's how it works. It's like a
Okay.
big,
Like,
yeah,
you are there in research, like.
yeah. So my work was research. So right now I
Oh,
also do research only. So for example, currently I'm associated with Chandrayaan mission also. So I'm in science team. So it's going to go to Venus in couple of years. So I'm only focused on science part. Like, okay, can we do this? Can we do this? How can we fix this? Can we do this? Engineering people will fix it. I'm not like, of course I'm an engineer, but not that engineer, right? I can not design this that thing. So
yeah,
yeah.
you are there.
So
Okay.
okay.
Sir, there is a one question on YouTube. The people are feeling bit left out on the YouTube. So
Okay,
someone
tell me.
is saying that I think the YouTube question will not be answered. The question is, without landing on the like in the Chandrayaan mission, we didn't land on the surface of moon. So how we just got to know the presence of hydroxide there and how these things are being able to get to know about
See, you
possibility of.
don't have to land everywhere, na? There is a technique called remote sensing, which we do, right? Like we have so many satellites around Earth also. You get your weather maps, weather forecast, right? That you get from satellites. From satellites, you know there is cloud, there is water, there is rain going to happen, radar maps, right? You get all these things. So you get from satellite. You don't have to actually go and measure it. So that we did from Chandrayaan 1, Moon Mineralogical Mapper, MQ.
Sir, I have
Any
a
other?
doubt.
Yes.
Nitzana, please ask it out.
Yeah, Nitzana.
Please
You
unmute
have to
yourself.
unmute. Nitzana, you have to unmute. Yeah.
Can you hear me now?
Yes.
Yeah. Sir, I am a first year EC student. So I
Mm-hmm.
wanted to ask you that, like, I really wanted to build a career in space science. I want to do astronomy.
Okay.
So, what skills should I start developing now to become useful in the planetary missions in the future?
Okay. See, astronomy is different.
Mm-hmm.
Okay. Astrophysics is different.
Yes,
So
yes.
all these things are different. So astronomy is like when you want to look at objects which are in deep space, like stars, galaxies, their movement, their motions, their interactions, and all these things. Astrophysics is like studying their things using physics, basically. Okay. So motions and gravity and all. You are in EC, electronics and communication.
Yes, sir.
Yeah,
Yes.
yeah. So the thing is, the best thing you can do is learn to design and build sensors. Okay, because
Okay.
sensors are very important for any missions. Any satellite you send, you have to send some sensors, right? It can be a
Yes.
radar sensor, it can be an optical sensor, thermal sensor, XYZ, whatever sensor. Everything what I have told today is all sensors, right? If you can
Yes, yes.
design a good sensor,
Hmm.
you will get hired. Trust me. Okay, because designing a cheap, efficient sensor is a demand today, is a huge demand today. Okay, so you learn that. So designing
Okay.
sensors, especially space grade sensors, not just normal sensors, space grade sensors, which can work in space in like high radiation environment and all that. So you have to be careful with that, right? So
Yeah.
learn designing that and try taking some courses and maybe pursue MTech or PhD in this field, designing sensors and all, and you will have a great career. And one more thing which you can do is learn to design this telescopes. You know, there
Okay.
are big ground-based telescopes we have. All these
Yes.
telescopes work on electronics, right?
Yes.
Automatically, they have to move with the Earth rotation and all that. So learn that.
Yeah.
Learn some mechanics, some physics along with it. You will be very better off if you want to do this. Okay.
Yeah. So one more question.
Quickly. We have a lot of
Yeah.
people waiting.
So like we have a lot of landings, successful landings, right? So like, what will be like another scientific question about the moon that the future India should be anxious about?
About moon?
Ambitious about answering the next question about the moon.
Okay. I never think like that. It's like a very, what I say, it becomes very uh, filmsy. You know, one
Hmm.
big thing which everybody is looking at, one this, one that. I think that, as I said, it becomes very filmsy. But again, if you want, uh, if we can land people on the far side of moon, or we can land a mission and keep in touch with that mission from the far side of moon, that will be a one big thing which we can achieve. So let's hope we can do it, I would say. But again, scientific, I don't think like that. So
Okay. Thank you, sir. Thank you so
yeah,
much.
yeah. Next person. Please avoid asking these deep space, black holes, and all these questions, because today let's focus on Chandrayaan and Moon. For that, we'll have some other sessions, because otherwise we'll get derailed and distracted too much. So let's just focus on Moon today. Okay.
Yeah,
Sir,
everyone, please make sure that. And Nandan, please ask it. Please turn on the camera and yeah, I'm just pinning you so you can ask it.
Mhm.
sir, how was the antenna system on Chandrayaan 3 designed to maintain a reliable communication link despite the lander's changing orientation and the rover moving around the lunar surface?
Well, as I said, I'm not that engineer, so I've not designed the antenna. But the idea is that's why you have an orbiter, okay? So orbiter keeps the link between the orbiter and the lander, okay?
Yeah.
Lander only. So lander is always looking at the orbiter and sending the signals and maintaining that communication. And the lander is maintaining the signal or link with the rover. So rover is going around and the orbiter sends the signal to the lander. Okay, so that way we communicate. So data gets stored in the lander and then lander sends it to the orbiter and orbiter sends it back to the earth. So that's how we do it. All right. Somebody said cannot understand because I'm a 9-year-old. What is your question? If you are a 9-year-old, I can. If you can ask the question, please put it in the chat. I'll try to answer. If you are a 9-year-old, I'll try to answer it in such a way, okay? So that you will also understand. Next. Anyone? Okay, we have
Yeah, well, can I?
yeah, Raif Khan, sorry. Raif Khan, please go ahead.
Yes, 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 yes. Yeah. Okay. Hello,
Mhm.
hello.
Yeah,
Am I
hello.
audible? Yes,
Yes,
yes.
yes, tell me
So
quickly.
my there are yeah, yeah. Okay, three questions. First of all, if you were to suggest us a book for high school and teenagers, which book would it be? A book to
Okay,
read.
about moon.
Yeah, about moon, about life, whatever. Just a book that you really like,
Mm,
really like.
uh, then you should read this book. I have it here. Yeah, it's called Pale Blue Dot.
Huh.
Pale Blue Dot by Carl Sagan. You will
Oh
get a
my God.
very, yeah, so it's a very interesting book. You
Yeah.
will get to understand humanity, our greed, our need, and why we are nobody. Basically, you will get a very different perspective. Why you should not bother
Okay.
about small things. So that is a very good
Okay.
start. And then if you want to study a little bit of more like black holes and space kind of things, then A Brief History of Time by Stephen Hawking. It's a very good book.
Okay.
There is no mathematics in it. It's a small book, but very good, very good. You get a good idea about a lot of things. Okay, so
Okay.
Sir, there is
And
a
Sir, I
one
have a
question
doubt.
by, hey, wait a minute, dear.
se-
Genius
and
physicist, sir, and he just continuously posting that
uh,
question. We
who?
just go through a genius physicist. I don't know the
Okay,
real name of it, Vedic, and he just continuously posting a single
yeah, yeah.
question.
First
Please
him.
check that chat
RTG
box.
or some what? RTG? What is RTG?
First answer him.
See, battery is like one thing. What battery we want is you want a nuclear kind of battery for missions which you are sending very far away from Earth, let's say. Then you won't have enough solar power. Then it's a problem. So you want to send a nuclear battery or something which will give you power for, let's say, 100 years. Okay. But if you have sun, you can send solar panels and a solar battery with it. And it's much cheaper and simpler to work with. So you don't want to overcomplicate. And then we also have space laws. So there are many space laws which govern the use of nuclear power in space. You cannot just send a nuclear battery if you want it. So I think you should. And as I said, you have questions about dark energy, dark matter. Please, we'll take it some other time. It's very complicated and it will take up too much time here.
I have a
Okay.
doubt,
Can
sir.
I continue?
Raif,
Can
you
I?
already asked a question. Please,
Yeah.
Quickly, one more question.
Yes,
Please
sir.
ask
Okay.
quickly.
No. I had two questions. First of all, you guys run simulations for this type of missions. So approximately how many simulations you have to run? And second of would be, I am interested in robotics. I have made many robotical projects. So if I were to create a rover, for example, only on the Earth, I like a representation of a rover. How perfect could I get it, and what type of modules should I require to make it representing the rover? Yes.
See, don't worry about rovers perfecting the rovers. See, there are, as I said, there are many groups out there. You can join them. Once you join the college, you will always have some clubs. There, you work with them, you design a rover and do your best. See, it's not like that you will get a perfect condition, but try to do your best. That's all. That's what we aim for. And then, like all the testing which we do for all these missions, we do it on Earth only, right? And then we send it and we hope for the best, right? So that's how you can do. And uh, what was the
How
other
many
question?
simulations? Yeah,
Simulation. See,
simulation.
there is no fixed numbers. It all depends on the complexity of the problem, the mission
Okay.
objectives, and X, Y, Z. So there are multiple variables there. There is no fixed number. Sometimes 10 is enough, sometimes 100 is not enough. So it all depends. Next.
Sir, I have a question.
And what
Yeah.
modules would have?
So I have a question.
Who is next? Sangamitra?
Yeah, I have a question, sir.
Yes, please quickly ask.
Yes, sir. Sir, so like when you were speaking about Chandrayaan mission,
Mm.
there were a lot of instances where you describe how the whole mission occurred. So if you want to pursue aerospace engineering as your career, then how do you analyze these past missions? If you want to learn about past missions, what is something that you should analyze? Should it be the mechanical side of it, or should it be why this particular mission was carried out?
See, I'm not an aerospace engineer. I'm basically a geophysicist who turned out to be a planetary scientist. See, the missions are, as I mentioned earlier, also, it's not one piece. It's all about learning how the multiple pieces come together and work. Okay. So from aerospace or whatever you want to work it's basically it boils down to this. How will you make a system work? How will you make these multiple pieces come together and work in synchronous way in such a way so that becomes a one big mission and a successful one. So that's how it should be, and that's how I would look into it. Anything next? Who is next?
Hello, sir. Hello.
Afaq, yes.
Hello, sir. Can you hear me?
Yes, yes.
I have a question, sir.
Please quickly ask.
Sir,
Mhm.
I have a question, sir.
Ask, na, please.
Sir, ISRO and NASA has also, sir,
Sorry, I didn't
has
get it.
also gone, and now they are working together. Will many companies together for the
Sorry, your voice is not clear.
project?
Please fix your audio. I cannot hear anything. Please fix your audio. We can go to the next one and.
Hello,
Sir,
sir. Hello.
okay, sir. Comment
Yes.
both the comment
Yes,
में
yes.
है.
Please put it in the comment.
Hello, sir.
Yeah.
Hello, sir. Can you hear me?
Yeah, I can hear. Who is this speaking?
Sir, I'm Jishanuddin Gaji, second year research student at ISER Behrampur, sir.
Okay, nice.
Actually, sir, I am currently doing my research on exoplanetary research and Martian planets, like life existence possibility and environmental conditions of Martian planet. So, sir, my question is from an astrobiology and planetary science perspective, do you think any cryosphere climate interactions could create or preserve any environments where microbial life might survive on Mars? Because, sir, I have read your research interest on cryosphere and Martian planets. That's
Right.
why, sir, I am asking that.
Yes, yes. So ICES are the best place on any planet or any object when you reach somewhere, ices are the best place to look for any kind of life form or habitability. And when I say life form, it's not means you will find aliens. It's basically microbial life. You know that you are doing the research, right? So
Exactly,
yeah,
exactly.
so people get excited, we'll find aliens. No, we are not finding aliens. We are just trying to find microbial life if we can. And that's why Europa is very exciting because underneath ocean, there might, underneath ice, there is an ocean. So there might be some microbes sitting there. So yes, ices are very interesting place. And that's why I study ices. And Mars ices hold a potential that maybe someday if we can dig deep enough, there might be a layer where you will have some microbes living there, right? So yeah, Mars is a very good prospect, and underneath the ice sheets, there is a prospect that we might find some kind of microbes. So yeah, keep
Yes,
studying, and if you
yes,
want, if you if
I,
you if you guys want to interact more, you can always write me an email or connect with me on LinkedIn. I respond to all the emails. Don't worry. So maybe you can get in touch with me over the email so we can
What
communicate
is your
better.
email?
Don't worry, everyone. I'll just share with you. Sir, I'm just
Yeah.
saying that
Google
there is
my
a one
name.
question.
Google my
Yeah,
name. Deepak Singh IT Bombay. You'll get it. My website and everything.
you'll get everything. By the way, we'll share with you, everyone. Please don't worry about that. Sir, there is a one question on the YouTube by Harsha Pathak.
Mhm.
How can one build a career after completing MSc in physics in the field of astrophysics, like PhD? What kind of the topic they can just choose, and the basic roadmap for.
Okay. So if you have an MSc in physics, that's the best thing. If you want to go in astrophysics, that's the best thing you can do. You should know physics to go into astrophysics. So look for opportunities where like astrophysics PhDs are offered. Of course, not many places in India, but outside, go for mainly Europe is very good. Like Max Planck Institute is there. In India, we have Indian Institute of Astrophysics, right? And some other places are also there. You can just these days Google will give you the list, and maybe you can ask an AI to give you the list of institutes. So they always publish their opportunities on their websites, and also on LinkedIn, you can follow some trends and some pages where they list these opportunities all the time. So you just apply to these opportunities. Go for PhD, and those PhDs actually they require a degree in physics. So you can apply for astrophysics and then go ahead and then do the research in astrophysics. That's like the easiest way.
So there is lots of school student on the YouTube, and
Mhm.
students really want to know about a book. Like there is a one kid is asking, "Sir, I'm a 9-year-old student. From
Mhm.
which book we have to start reading about the space or moon or anything like that?"
Okay. I don't remember the name. I just bought a book. Give me a second. I'll find it for you guys. So for my son, I have just bought a book. Like a set of books are there. So you can actually start from there. Let me see. Where is it? Okay, so there is a 8 book collection. It's called Space Encyclopedia. Okay, it's a very nice
Yes.
collection. There are 8 books there. Okay, I'll just put like the thing here in chat. Okay, so you can search for it. It's a encyclopedia of space. If you are like 9, 10, 11 years old, that age, under 15, you should start with this. And there is a, as I said, there is a 8 book collection. So you will get to know almost everything from very fundamentals and in a very easy language, because encyclopedias are designed for kids only, right? So you get to learn a lot of things. So my son is like only 8 years now, so I've got these for him. So you can learn from it. It's very interesting, and a lot of nice, cool pictures are there. So you get to see things. So go ahead, okay?
Okay, so by the way, there is a one more person, San Mitra, and he or she saying that I'm presently doing research in astrophysics. What is
Mhm.
about the future missions? I really want to know and what to get to
See,
know.
future missions, I cannot give you a list. I can, of course, tell you about few things about ISRO missions. Like ISRO is planning a mission to Venus, which I am part of. So Shukran is will be there in couple of years. Then we are also planning to have like Gaganyaan, means we are going to send humans for Indians in space, right? and then we are also planning to have our own space station. Like we have International Space Station ISS. We are trying to have a Bhartiya Space Station BSS in near future, and by 2030 or something. So these are the few missions which are in pipeline. We are also planning mission for Mars, another Mangalyaan. So these are some missions which are planned for near future. And then for, of course, long term, we are planning missions for like Europa and all those Jupiter missions and all. So currently, we are also planning to build a space observatory, like we have James Webb, right, from US and all. So we'll are planning to have our own observatory in space, a telescope in space. So these are some of the missions which we are planning.
Excuse me.
So, yeah, Astos, please ask it out. Yes, yes, yes.
Yes, I am 11 years old currently. I've been studying about aircraft for the past 4 months, I guess. I like this topic that that India is doing currently, called the AMCA project with France and like fifth and sixth generation aircraft. Do you know anything about it?
No, because I'm not like an aircraft engineer, so I don't keep tap on like what is currently happening. But see, it's not just France or anything. We have ties with Russia also, US also. So that is not the thing. The thing is, if you want to learn about that, go ahead, read some books. There are a lot of good courses available online. Like there is a SWAM portal, NPTEL portal, right? So you can learn about those things. So these are free material available. You can learn from YouTube also. So learn from it. You are too young. Don't worry about like what the future will be, how you will get into this, that. Don't worry about it. Keep learning. And then once you get to the class 11th or 12th, then you start looking for institutes where you can apply and get a degree. And initially, it is all about learning fundamentals. So you should learn about physics and maths. Those are two crucial things.
Sir,
Okay.
I was learning physics and chemistry and maths also. I have started like a few months ago. Like I also researched about Mars missions, like Ingenuity and Perseverance rovers and Chopper.
So all those things in a different session, right? Today we'll talk about moon only and missions. Like that's it.
You might have heard about the Artemis 2 mission, right? Like I didn't understand what they did. Like were they just looking at the moon and then taking like pictures of
See,
it?
it's like a mission. They wanted to communicate from the far side of the moon. That was the main objective.
I heard that they're mapping the surface for something. Like, was it
See,
for that?
if you are making a mission, we are spending so much money, you are going that far. Why don't you take some images also? Some data. Why won't you collect it? So that's what they're doing. So, but they have sent humans around, made that orbit around moon and come back and see the communication systems, navigation systems, and now they are planning to send actually humans to moon and land them on moon. So the idea was just to go there, get a feel of it. Okay.
Okay, sir.
Okay. Next, we'll have a couple of questions.
Abhimanyu, please ask it out and yeah, make it quick because this is your second time.
I think Abhimanyu has already
But
asked,
sir,
right?
I have two doubts in the Chandrayaan 2 mission. Which phrase went wrong? Like which one?
Sorry, I told you guys already. Please don't ask same questions again. I have already told you guys. So please, there's no point in repeating questions.
So I think there is no more questions. So is there anyone want to ask any other question? Everyone, please let me know.
If you have anything from YouTube,
I have a question.
who is speaking, please turn on your video.
Yes, sir. There is a very interesting question from YouTube, sir. I really. Okay.
Please
So
read it.
someone
Then
just.
yeah.
Yes, sir. Someone just
Can
asking
you hear me?
is
Savik, wait. Let me go through this question and then I'll come to you. Okay.
yeah. So basically, there is a Sandy and who is asking the sir, is entrepreneurship is a good option for profession? I'm planning to become an entrepreneur when I just grow up. It's completely off.
Entrepreneurship.
Yeah.
If you want to be an entrepreneur in space science, yeah, sure. Why not? We have like Skyroot launched a couple of months back, right? And then we have a lot of exciting satellites coming up, payloads coming up from private companies. We have companies like Galaxy. Yeah, Galaxy, not Galaxy, Galaxy.
Galaxy. Yeah.
Yeah, so they just twisted it a little bit. Galaxy I, they combined together. So Galaxy I is there. Manastu Aerospace, I think, or something is there. Manastu. They are based out of IT Bombay now. They are situated in Mumbai. So the student was from IT Bombay, Manastu Space or Aerospace, something. I'm forgetting the exact name. So you can search. There are so many companies which are coming up. They are doing really good. They are earning well, and they are hiring a lot of people. So you can also think of a problem which you can solve in space sector. Um, as simple as making something cheaper. That will do good, right? So there are many things you can do. So entrepreneurship is very exciting, especially in space sectors. A lot of companies are coming up. You can take inspiration from these examples I gave you and come up with something. And if you need my guidance anywhere, you can let me know. Connect with me. I'll be happy to help. Okay. So
Souvik,
Souvik,
please.
yeah, Souvik was asking something.
Yes, sir. Like, what kind of technologies, like instruments we're gonna use in Mangalyaan 2 mission?
That is not finalized yet. See, when a mission is planned, what happens? We ask for proposals, basically from academia, from different institutes, wherever you have people working on these fields, and then the team or committee will look through these proposals, and they will see which instruments will be feasible and are consistent with our future goals. So that way we will first they will shortlist. So let's say there are 100 proposals. So first 50 will be shortlisted. Then 50 will be asked to come and give a presentation. Then out of 50, 20 will be shortlisted. Then further discussions will happen. Then we keep on filtering. And then, as I said earlier, like very first, somebody asked me a question, right? That there are different teams. Then there are engineering constraints. So sometimes a payload or instrument might be very good, but it might not fit well with the engineering constraint we have. So that might not go. Then we will go for the next one. So that's how it is decided. So it takes very long time before finalizing any mission. So we don't know yet what we are going to send. But for example, I can tell you about Venus, like we are planning to send a SAR instrument. SAR is synthetic aperture radar, and that nobody has ever done for Venus. So if we can do it, it will be a big step. And that will provide us a lot of new data, which is not there earlier. So that is kind of we want to do, right? So that's how things are decided. So there are going to be like 10, 12 different payloads, depending on different constraints we have. All right.
Yes, sir. Yes, sir, are we planning for any space telescopes?
These are things in the pipeline, but when actually they will happen, we don't know. It all depends on the current situation, funding, like, and what is urgent currently, what we need to do now. So things change. So that's how it works. It's never certain. That's the thing with planetary missions or space sciences. It's not certain. It changes, and it's all dynamic, and that's the beauty of it. You keep changing things depending on how the situation is and what needs to be done. All
Okay.
right.
Sir, I think almost done. So there is only
Yeah,
one person called Saksham. Then we'll just end this session here on this.
yeah. One last question and we end this.
Saksham, please turn on your camera and ask your please. Mic as well. Saksham.
Sir, so am I visible?
No, but you're audible. Please go ahead. Ask your
You're
question.
audible.
Okay, sir. So I had a doubt that why does all the space rockets are painted white? Like
Think,
I saw rockets of Israel, and almost all of them are painted white. Why is it so?
think common sense. White reflects more. You wear white clothes in summers, right? You go out, you don't want to wear black. You will be too hot, right? So simply you paint everything white to reflect solar heat, solar energy, or solar whatever is coming, radiation basically, what we call, so that you have less heating. Less heating means less cooling you require. Less cooling requirement means less energy you will require. So you will have to send a smaller battery.
And sir, I had one more question that why does ISRO has so less space launch systems?
Sorry, I didn't hear it. I can't. Somebody else is also speaking.
Sir, my question was why does ISRO has so less space launch systems?
So less?
Yes, sir. We only have three: PSLV, GSLV, and LVN3. But why does it so? It also makes us to force to do very less missions.
No. See, within those we have multiple subcategories also. It's not like we have only one PSLV. We have different categories of PSLV because depending on how far you want to go, right? So GSLV is geostationary launch vehicle. So that will take you to 36,000 and all. But then you have also planetary, these ones. They will take you for, let's say, for moon and all, for Mars mission. So you have different rockets for different missions. It's not only that much. I showed you for Chandrayaan 1 today. Sorry, Chandrayaan missions today. Okay, so there are many different types of rockets. We have different capabilities, different thrust, different power. So all these things are there. All right. Okay, one chat question is interesting, so I'll just answer this and then I'll end it. Is this ozone layer on Earth and all that? So of course there is no ozone layer on Moon. So we cannot avoid or reduce the risk of it. The thing is, you have to have some protective suit with you. That's why astronauts wear all those protective suits. You not just ultraviolets, you will have X-rays, right? So all these high energy rays which are coming from sun and also from outside our solar system is going to hit us or any object there, basically. So to protect it, you have to have some kind of protective gear with you. So you cannot avoid it or reduce it. Now to grow plant on moon, how will you grow plant on moon? It's like near impossible. You don't have oxygen, any air. You don't have any kind of carbon dioxide to consume. You don't have water. You have water molecules, which I told you about, but not water to have growth of plant, right? So you don't have anything except the soil. And soil is also not like very fertile like Earth, because our soil is formed in a very different way. On moon, it is just parts and pieces. So we pretty much cannot grow anything unless we make like a dome or something where we change conditions in such a way so that we can grow some plants. But right now, no. So that's where I'll end, I guess. It's been a very exciting session. Thank you all for it.
Sir, we'll just wrap up it here only.
Yeah.
Okay, so as usual, I'll just request everyone to please turn on the camera and thank you so much, sir. It was really nice session again.
Sir, I have one more question.
Please,
yes.
You can email me later. I'll answer.
Everyone, I'll just tell you one more thing. I'll just share the whole contact of the sir. You can just search his name as well. You'll just find sir's email, LinkedIn, Facebook, Instagram. You can just connect anytime.
Yeah.
Please
If
don't
you want to connect on Instagram, then I'll give you.
Sir,
it's deepaksingh.space. Okay.
Okay, everyone. So please turn on your camera. So you could just capture this moment as usual we do, and then we'll just end this session here. Okay. Okay. Okay, everyone. So thank you so much for joining, and especially thank you so much, sir, for coming and giving your time. It was really nice session as usual. Sir.
Okay, thank you. Thank you. Bye bye. Good night, everyone.
Bye, everyone. Good night.
Thank you so much.
Thank you so much, sir.